Hello, and welcome to section 5.2, day 2, properties of rational exponents and radicals. Today we're going to go through and simplify some radicals, rationalize some denominators, and combine some like terms. All right. The biggest thing that I would say to you guys when you do this is think of radicals like variables. We can't combine them unless they're the same root and the same number inside the radicand. Okay. So we look at the first one. I just want to start off at the top of the page and kind of talk about if I gave you the square root of 50 and asked you to simplify it, we would simplify that to be the square root of 25 times the square root of 2, which would be 5 square roots 2. All right, the reason why I want to get into start is we're going to do the same thing with some of these now, except we're going to have other roots. So it'll be really helpful to have our chapter 5 cheat sheet so we can go through and look at our perfect either cube roots, square roots, fourth roots, or so on. All right. When I look at the cube root of 135, all right, I've done this a little bit longer, and I know that this is going to simplify to the cube root of 27 times the cube root of 5, okay? If you didn't know, you could just go through 135 and divide it by your perfect cube roots. 8 doesn't come out to a whole number, and then 27, and notice it's 27 and 5. Why do we do that? Well, we know the cube root of 27 here is 3. We don't know the cube root of 5, so that stays. So our answer is 3 times the cube root of 5. Okay. The next one, we need to rationalize the denominator. If we need to rationalize the denominator here, we need to get rid of the radical. How would we get rid of square root of 2 in the denominator? We'd multiply it by the square root of 2 over the square root of 2. We multiply the numerators, that would give us the square root of 30 over the square root of 4. Well, the reason we do this is, what's the square root of 4? The square root of 4 is really 2, so we don't have a radical in the denominator now. Okay. Example C is very similar to B, except now we're talking about fifth roots. Right? When we talk about fifth roots, we need to make sure we remember, well, what's a perfect fifth root that we know? Well, a perfect fifth root that we know, all right, is 32. All right, so we have to think, well, what can we multiply 8 by to get 32? 4. 4 times 8 is 32. Similar to this one, we'd multiply the top. We'd have the fifth root of 28, 7 times 4, over the fifth root of 32. We know the fifth root of 32 is 2, and we leave the numerator as it is. Once again, notice we got rid of the radical in the denominator. Okay? For example D, we need to think about the fourth roots we know. Well, we know the fourth root of 16, all right, and 160 divided by 16 would be 10. The fourth root of 16 is going to be 2 times the fourth root of 10. All right. Now to stay consistent when we do this, because we took an even root, I should do plus or minus. If you don't, it's not a big deal. We'll talk about how certain problems will tell us we need to do that or not. Okay. All right. Now this is when we want to have like terms or like radicals when we do this. For radicals to be similar or like radicals, same root, same number inside the radicand. So in this case, we're taking the fourth root of 10 in each of them, so we can combine them. The number in front of this is 1. Well, 1 plus 7 is 8 times the fourth root of 10. And that's your answer. Okay? Just like if you had x plus 7x, that would give us 8x. The same exact thing as if we had variables. All right, notice for example B, they're talking about 7 to the 1/3. They're both 7 to the 1/3. It's really a cube root, but we can leave it like that. 5 minus 6 is -1 times 7 to the 1/3. Obviously, you wouldn't have to write the 1 there because the 1 in front of it's implied. So either of these two would be acceptable answers. Okay. When we start to look at example C, all right, we notice something here. They're not the same number inside the radicand. So sometimes if it's a case like this, we're going to need to simplify what's inside first. Well, if I have a 4th root of 3 here, I'm probably going to divide 48 by 3 to realize it's 16 times 3. All right, well, what's the 4th root of 16? It's what we know, which is 2. So we now have 2 fourth root of 3 minus the 4th root of 3. 2 minus 1 is 1. So you could either write it as 1 times the 4th root of 3 or just the 4th root of 3. Okay? Those would be the ones with the extra step where it's going to kind of combine simplifying the radical and combining them. Some of them aren't. All right? Example D is similar to example A. All you're doing is just subtracting because you have the same root and the same number inside. 5 minus 8, negative 3, cube roots of 13. All right. Example E is similar to B. We have 9 to the 2/3 in each of them, so that's the same. 4 plus 10 is 14 times 9 to the 2/3. All right, we're not going to multiply these things. Remember, you'd have to do the orders of operation first. That's why we leave it as is like that. Okay. Example F is very similar to C. So when we go through and do this, I'm going to have to simplify the cube root of 40. Well, the cube root of 40, and we have this cube root of 5 here, so that's going to be our hint. If we divide 40 by 5, it's 8 and 5. Well, what's the cube root of 8? It's 2. So now, our like terms here, if you notice our like terms, are these two because they're both the cube root of 5. 1 plus 2 would be 3 times the cube root of 5 minus the 4th root of 5. Now notice, this is a cube root and this is a 4th root. They're not the same root, so we can't combine them, and that's where our answer would stop. Okay. If we scroll down to the next page, we'll see some examples of these where we're going to have to simplify some of these radicals. We're going to assume all variables are positive. If they tell us that, anytime we take an even root, we now don't need to say plus or minus. All right, so as we go through this is going to kind of go back to the part we need to know our properties of radicals, where the numerator is the power and the denominator is the root. Okay, so when we look at the first one, I'm going to separate each of them first so we can see it. So this would really be the cube root of 2 times the cube root of a to the 13th times the cube root of b to the 3rd times the cube root of c to the 8th. All right. I'm going to rewrite the radicals involving variables as rational exponents. So this would really be a to the 13 over 3, b to the 3 over 3, and c to the 8 over 3. Okay? Well, the reason I do that is when we go through and look at this, how many times can 3 go into 13? It can go into it 4 times. So when we do this, it's really a to the 4th, and we'd have an a to the 1/3 left. B to the 3 over 3 would be b to the 1st. And if we did 8 divided by 3, 3 goes into 8 twice. All right, oops, sorry, let me get rid of that. With how many left over? With 2 left over. Oh, sorry, so this would be c to the 2/3. All right, well now when we look at it, anything that has a whole number exponent is going to come out in front. So we'd have 4, or a to the 4th, b to the 1st, c squared. Now if we think about our a to the 1/3 and our c to the 2/3, both of those are saying cube roots. So we'd have the cube root of 2, which is in our radical here, our 1/3, and our 2/3. So it would be a to the 1st, c to the 2nd. All right. I know it seems kind of confusing. I think writing it as rational exponents here help. If you want to write this first one as a rational exponent too, as well, you could. All right, to understand that that's how we got them all inside the cube root. Okay. All right, when we look at example B, we need to rationalize the denominator. Our goal here is to get our denominator to be y to the 15th, all right? If we get it to be y to the 15th, 15 divided by 3 is 5. So what would we have to multiply y to the 13th by to get 15? We'd have to multiply it by the cube root of y squared. If we multiply the numerators, we would have x squared times the cube root of y squared over, well, the cube root of y to the 13th times the cube root of y squared would be the cube root of y to the 15th. Well, we know that this is really 15 over 3, which would end up being y to the 5th, okay? You won't have a lot of those, but it's just important to understand that we want to make sure we can get rid of the radical in the denominator, and that's why we need to get this exponent in the denominator to be a multiple of 3 to be able to get rid of it. All right. When we look at example C, I like to separate them all to see them individually first. So I'm going to take the coefficients or the numbers here and do 16 over 8 times x over x to the 2/3 times y to the 1/3, it's really over 1, times, well, 1 over z to the -4th. It's easy for me to see here how I can simplify each of these. Well, what's 16 over 8? That would be 2. If we have x over x to the 2/3, the bigger exponents in the numerator, it's a 1. We'd bring it up. 1 minus 2/3 would be 1/3. We can't do anything to the y to the 1/3. And then how would we make this -4 in the denominator positive? We'd bring it up to the top, and we'd have z to the 4th. This is an acceptable answer. We could also write it as 2z to the 4th times the cube root of xy. All right, that's just because, notice once again, the numerator is the power, the denominator is the root for each of those. That's how I got the next one there. Okay. Example D is very similar to C, so I'm going to separate each of them again. All right, 6 over 3, once again, is 2. We have x over x to the 1/2. So if we bring that up, that'd be x to the 1/2. And the y in the denominator, all right, is 1/2. So we need, that would now be y to the 1/2 in the denominator. If I rewrite this in radical form, this would be 2 the square root of x over the square root of y. Now what I need to do is rationalize the denominator here. Oh, my bad, I don't need to do that. Sorry, go back. I didn't see the y there. All right, I was making the problem a lot harder than I need to be. We have y to the 3/4. Okay, so when we do this, we'd still have our 2, x to the 1/2. Well, 3/4 is bigger than 1/2. All right, so if we were going to subtract these, we would do 3/4 minus 1/2, which is really 2/4, and I'd get y to the 1/4. That is my answer. A lot nicer than what I was going to do in the first place. All right. All right. So looking at example E, we're going to separate everything. The 5th root of 64 times the 5th root of x to the 7th all over the 5th root of 243 times the 5th root of y to the 15th. All right. Well, when we talk about the 5th root of 64, right, what do we really know that to be? Well, Well, that is the fifth root of 32 times the fifth root of 2. And I'm going to rewrite this one as x to the 7/5. What's the fifth root of 243? 3. And I'm going to rewrite this one as y to the 15/5. So what I'm going to do now is I'm going to simplify these things. If I simplify them, what's the fifth root of 232? Or sorry, what's the fifth root of 32? Sorry, it's 2. That's going to go on the outside. How many x's can I take out if I have 7/5? I can take out 1x. And that leaves me with a 2x squared. Right? If we go down, if I'll just do it down here, to the 7/5 would be x times x to the 2/5. 2/5 is the second power, fifth root. All over 3 y to the third. All right, so it's important we think about it like rational exponents to make our lives a little bit easier. All right, last one. I think we'll end on an easier one here. We still separate them. We don't know the fifth root of 4, but if we wanted to write each of these other ones as rational exponents, that's what we'd have, okay? And I'm just going to keep the fifth root of 4 here out in front. So I'm going to say it's going to be the fifth root of 4. How many times does 5 go into 8? It goes into once, with how many left over? 3. How many times does 5 go into 14? 2, with how many left over? 4. And how many times does 5 go into 5? Once. All right, so anyone that has a whole number exponent, our a, our b squared, and our c goes out in front. Now what's going to be left in the radical would be the fifth root of 4, this one here. Oh, there should have been a b there, sorry. All right, the a to the third, because it'd be the 3/5, and b to the 4th. All right, so I know it can be kind of confusing, but if you write them as rational exponents, I really think it helps. All right, your homework will be posted soon enough. If you have any questions, please let us know. Have a great day.